Okay, everybody, you're all very welcome to this seminar this afternoon, both of you who have joined us live and a couple of hundred in the future who will join us on our YouTube channel. I was so pleased and delighted, in fact, when Marcus agreed to run this training seminar for us. As many of you will know, I'm relatively new to radio astronomy, and I very quickly discovered that GNU Radio would be a very powerful tool. And then I looked further and discovered how steep the learning curve was. But at the same time, I found many references to our speaker this morning. And so, Marcus, I'm very grateful that you've given up your time to share with us. And it's over to you. Our screens are yours.
Well, thanks very much for inviting me. I'm not sure, to be honest, that I'm going to be able to fill 3 hours, but you know, it depends on the questions and the sort of side trips that we take based on those questions. So the format is going to be that I'm going to give a presentation, and then we're going to launch into actually diving into an example GNU radio flow graph that is for radio astronomy. I built it just for the purposes of this seminar, but it's perfectly useful for radio astronomy. How many of you actually did the pre-work and are actually able to follow along?
Regrettably, I wasn't able to.
I have an installation on a Raspberry Pi, but I didn't have the opportunity to do the pre-work.
Okay, well, regardless, it should still be elucidating for many of you, and the flow graph itself is reasonably well documented, and you know, you should be able to work on it on your own afterwards if you choose to. But as I said, it's actually useful. It can actually do real things. So people should be able to learn a lot from it and use it as a springboard. So I'm going to share my screen now and go into the presentation part. Oh, it says host disabled screen sharing.
Yeah, sorry, that's my fault, of course. It should work now.
Okay. Okay, how's that? Are people seeing my screen?
Not yet. That looks good.
Okay, so then I will start this slideshow. Okay, so we're going to talk about GNU Radio and radio astronomy. I'm calling this presentation part 1. I've been invited to do part 2 of this, I think in January of 2022. And at that point, we'll have follow-up on this one, questions that people have come up with over time. Of course, you're always free to ask me those questions directly in the intervening time by email or other channels. But part 2 will cover probably interferometry and maybe a couple of other topics. This is the basics. We're going to talk about radiometry and spectrometry. So there's kind of a history with software-defined radio and radio astronomy, somewhat independent, at least initially, of GNU Radio. There's been a very long road to acceptance of SDR in radio astronomy in both the professional and amateur communities. That has obviously changed in the last few years. I published, as far as I know, the first paper on SDR and radio astronomy back in 2004 at the EuroSETI meeting in 2004. And for almost a decade, I was the only person using SDR techniques in radio astronomy. I was generally thought of as a bit of a kook, which I was, you know, perfectly happy to be thought of, because the tools that I was using and the techniques I was using were perfectly viable and they worked for me. And I just assumed that the rest of the world would eventually see the light. When the RTL SDR became a thing several years ago, that changed actually relatively rapidly. I published a couple of papers on how to build yourself a cheap radio telescope with an RTL SDR and a used DBS satellite dish and so on. And others actually at approximately the same time did the same thing. I think Peter East did one. The folks at Haystack had a grad student working on that. So the introduction of the RTL SDR was sort of a sea change in the attitudes about SDR and amateur radio astronomy in particular, but radio astronomy in general. So now there's lots of people producing software for SDR and radio astronomy, most of them GNU Radio based. Other ones other than ours, the Virgo software from our Greek friend, the West Virginia University RAIL, which is the radio astronomy laboratory. They have some GNU Radio applications, mostly tailored to sort of amateur and small scale efforts. Of course, CCERA, which is me and my friends. We have a Git repository with lots of different bits and pieces of GNU Radio software for various aspects of radio astronomy. And there are others out there. I can't list them all. The very earliest releases of GNU Radio had in-tree radio astronomy applications. In the early days, I think all of the applications that use GNU Radio were actually kind of bundled as examples. We eventually divested them because it was difficult to manage the applications and the basic platform as a single unit. So the early radio astronomy applications were cleaved off of GNU Radio, and I developed them and evolved them over many years. And they changed and they evolved, and they're not at all like they were in the very early days. So GNU Radio itself, it was actually first released around 2001 as an offshoot of a MIT project. And of course, has grown significantly in use and capabilities since that time. There's dozens of developers contributing to it. There's hundreds of different applications written with it. And there's thousands of users of GNU Radio-based applications. Most of them, of course, not radio astronomy based. There's the GQRX, for example, which is a kind of a generic general coverage receiver, very similar to what you'd purchase as a hardware object 20 years ago. GQRX turns your laptop into a general coverage receiver using whatever SDR hardware you happen to have. GR Inspector, for example, is used for what one might call hacking unknown wireless protocols. You've encountered a signal and you're not sure what it is. GR Inspector is an application that uses GNU Radio to help you sort of untangle those signals and figure out what they are and hopefully demodulate and decode them. And dozens of others. As I said, CCERA has quite a number focusing on radio astronomy, and the GitHub address is given there. So essentially, what is GNU Radio? Primarily, it's a development framework, the highly specialized development framework for digital signal processing applications, mostly in the radio space, but GNU Radio itself doesn't really know that it's connected to radios. It's actually been used for sonar. It's been used for high-speed sampling of mechanical vibrations sensors in a steel mill, for example. They needed to produce some very high quality steel with very precise structural properties. So they attached an array of sensors to the I-beams that they were producing and used GNU Radio for doing the signal processing, granted at relatively low rates, like a few kilohertz sample rates. But it does show you that GNU Radio, because it's just a generic DSP framework, can be used for all kinds of signal processing applications other than for radio. A lot of people, when they first encounter GNU Radio, think it's a radio with a lot of knobs. And so they are often off-put by the fact that there's a very steep learning curve and can't understand why it's just a radio. I should be able to figure out how it works, and not really realizing that it's actually a programming environment. It's actually a development framework. It's often been sort of mismarketed by the naive as a radio with a lot of knobs, but that's definitely not what it is. So GNU Radio programs are in the sort of formal computer science sense, they're called directed graphs of individual DSP blocks. So you can imagine a bunch of blocks laid out in a graph that achieve some specific function. And this is very similar to, if you're familiar with radio hardware, you would probably decompose the hardware into different blocks that do different things. There's RF amplification and mixing and down conversion and demodulation and audio processing or whatever. Maybe it's data processing. You know, maybe your demodulator is actually for data and you do lots of other processing, but you can think of it as like a chain of functional units. And GNU Radio, that's what it does. It's like a box of parts that you chain together and perform useful functions. Most of the blocks are written in C++. A lot of those blocks are what I describe as ruthlessly optimized, and they use the vector capabilities of the underlying CPU if it has those capabilities. So it's actually, despite the sort of computational model, which some people think is a little bit inefficient, there's sort of a string of pearls model, it's actually quite a high performance framework because of the fact that most of the core blocks are written in C++ and have been pretty well optimized over the years. The Python aspects of GNU Radio are what I would call the control plane. The samples, for the most part, don't flow through Python at all. Python never has to deal with the samples. It doesn't have to marshal them and unpack them and repack them and all of the things you'd expect to have to do with Python dealing with these raw samples. It's just a control plane. It's used to establish the elements of the flow graph, but those elements and the buffer management and the thread management is all done in C++. And inside the base code, the code that you get with just the GNU Radio source code, there's dozens and dozens of different processing blocks included in the base code. And not surprisingly, almost all of them involve what I call the works of man, telecom and wireless and radar and all of that stuff that's really utterly unrelated to radio astronomy. So the question then becomes, why use GNU Radio to do what we do? So at its core, also, are there any questions before I move on? No, okay. So at its core, GNU Radio is what we call a multi-threaded scheduler and a ring buffer manager. That's what it does at its core. And it also has this palette of blocks that you can kind of plug into the scheduler and the ring buffer manager and do useful things with. So just those two things, the fact that it's a ring buffer manager and a multi-threaded scheduler is already a huge thing. Because if you're writing particularly high bandwidth radio astronomy applications, you're going to need those things anyway. If you decide, oh, I don't want any of this, I'm going to write it all myself. If you're going to do high performance, high functionality radio astronomy applications, you're likely going to have to do some version of this anyway. So it's already there. There's plenty of standard blocks that come with GNU Radio that are actually useful for radio astronomy. They're very generic. They're not tailored to one particular communication standard or communications technique. And because those blocks are already there, that also makes it useful for radio astronomy. GNU Radio has the concept of what's called an out-of-tree module, or what other environments may call a plugin. So we're not going to go into out-of-tree modules today because it's a little bit arcane, and we may go into it in part 2. But it's a mechanism for writing your own blocks and having them available to GNU Radio to plug into the framework. There's also a concept which we are going to touch on today called embedded Python blocks, which is when you're using GNU Radio Companion, you can write your own block in Python, right in GRC as if it's just part of what you're doing. And it has all the properties of a regular processing block, except it's executing in Python. So they're generally not used for high-speed stuff, but that's okay because most of the back end of most of amateur radio astronomy doesn't need to run very fast. It's only the front end bits that are dealing with wideband IFs and RFs and FFTs and all of those things that need to operate at relatively high rates. The back ends, typically used for logging and sort of cursory analysis and so on, very often only need to operate at, let's say, a few tens of events per second, which is just perfect for Python. So I mentioned GNU Radio Companion. It provides a graphical flow layout tool. We've talked about a flow graph, which is just the directed graph of blocks. It's very similar to, if any of you are hardware people, and I suspect some of you are, like a schematic capture tool in the hardware world, where you drop down components and draw connections between them. Well, GNU Radio Companion is very similar to that. Excuse me. And it makes quick experiments quite painless, at least for me. There's still a learning curve, I fully admit, but you can have a thought. You can say, oh, what would be really cool if I took the signal and did this with it? Well, GNU Radio Companion allows you to do that kind of experiment, typically without writing any code or only writing a minimal amount of code. You just have to, slam these blocks together to do the thing that you want to do. So as I said, it's a graphical tool for laying out these flow graphs. Any of you who may be familiar with Simulink, which is part of MATLAB, or LabVIEW from National Instruments, will kind of recognize the sort of overall presentation and the overall concepts in GNU Radio Companion. It uses what is called in computer science terms a data flow model of computation. It's not a procedural programming environment in the usual sense. Usually all of your procedural stuff, your if then else, your explicit, mathematical expressions and all that stuff is hidden inside a GNU Radio block. And GRC provides this sort of higher layer data flow view of all of that stuff. Along with that, it has a what's called a dependency evaluator. And that's pretty typical with a data flow model, because it's what's called non-procedural. You need a way of maintaining the relationships among variables and parameters within the data flow. And that's where the dependency evaluator comes in. So it allows block parameters and variables to be consistent with one another. If a block parameter relies on a chain of variables, for example, if you update one of those variables in real time, the block parameter will get updated automatically because of the dependency evaluator. Now, you don't need GRC for making flow graphs. GNU Radio was born without GRC, and you can manually code all the Python, all the connects, and all of that stuff. You can do it manually. You don't need GRC, and some people do that because they don't understand the point of GRC. Those are people I would describe as having extremely strong memories, because you can imagine a flow graph with, let's say, 30 or 40 blocks in it with connections all over the place. And those connections are actually represented by lines of code that call these connect routines inside GNU Radio. Keeping track of all of those connections manually in open code becomes very difficult very quickly, in my experience. There are people who just keep it all in their head and are able to. I'm not. So GRC is very useful for that. But GRC did enter the scene several years after GNU Radio was already under significant development. All of my early radio astronomy work with GNU Radio was done without GRC. It was done manually and laboriously. I was very relieved when GRC came along. It was a breath of fresh air in this space. So I've talked about the dependency evaluator, and we are going to abuse it just a little bit in the example today. I used to, and I still do in some of my older code, I use the dependency evaluator a lot to sort of cheat so that I didn't have to write blocks. Again, I mentioned a lot of the back-end processing in radio astronomy only needs to operate at a few hertz. So there are what amount to polling functions in GRC that allow you to sort of abuse the dependency evaluator to update things on a regular basis without having to write a block that kind of plugs directly into the sample stream. Now that GRC has the embedded Python block concept, a lot of that abuse of the dependency evaluator can go away. And in fact, the example that we're going to explore today only uses the dependency evaluator and the function polling and so on for one very specific thing. And the things that traditionally I would have used that for are now done in embedded Python blocks. Even newer versions of GNU Radio, 3.9 and later, allow insertion of what are called code snippets into the generated code. And that relaxes even further the sort of pure data flow model that was previously enforced by GRC. It allows you to do some things that previously you might have to edit the generated code and sort of insert bits and pieces into it after GRC had already generated the code, which is ugly and hard to maintain. So they invented this concept of code snippets, but it is for GNU Radio 3.9, and today we're going to be using 3.2 because that's what comes with Ubuntu 2104. And a graphical representation of the signal flow is really useful, particularly if you're from a hardware analog background. You may be used to that sort of view of overall functionality already, and GRC kind of gives you that. Any questions? So now we move into what exactly is an amateur radio telescope, and this talk is unavoidably focused on amateur radio astronomy and the kind of relatively simple problems that you're solving with an amateur radio telescope, which is not to say that this stuff cannot be used in professional radio astronomy, because it has been. It's just that the scope of the talk needs to be sort of tractable today. So a typical amateur radio telescope is like a single pixel radiometer. It measures the brightness over a single part of the sky, typically, a fairly fat pixel, depending on the size of your antenna, and also sometimes they're used as a spectrometer to basically give you spectral information over that same, very fat pixel on the sky. More advanced amateur radio astronomy people, they might venture into interferometry or even pulsar detection, but we're not going to talk a lot about that today. I will say that if you're just starting out and you have budget for, let's say, an instrument with a 12-foot dish, you might actually consider using 2 6-foot dishes or 8-foot dishes and building an interferometer instead, because they are extremely useful and they don't tend to suffer from the same problems as single dish instruments. And you can actually get much more satisfying results much more quickly with an interferometer, but we're going to talk about sort of the mechanics of that in a future talk. So these are all the things I mentioned are relatively easy to implement using GNU Radio, but you still need some programming and DSP knowledge. That's one of the things that people run up against with GNU Radio, is the GRC makes it seem like You don't really need to know much of anything to start doing some incredibly useful things. And I would say that's not entirely true. It's kind of a seductive perception of GNU Radio and GRC. You do need to have some programming acumen. You do need to understand some DSP concepts. And you need to remember that GNU Radio is basically, it's a programming framework. So what is a software-defined radio in sort of, 3 sentences? A software-defined radio has some RF gain. It does some down conversion to a complex baseband. It has some high-speed complex sampling, and the bandwidth of the instrument is more or less defined by the sample rate that you're using. Some SDRs can support sample rates, right up into the nosebleed section. Some are more modest, like the RTL SDR, and to a certain extent, it just depends on your budget for both the radio and the computer that is consuming all of those samples. GNU Radio, as I mentioned, complex baseband signaling. I'm not going to go into a lot of what that actually means here. I've given a link to a site that is one of the dozens of different explanations of complex baseband or IQ signaling out there. And people are free to explore that at their leisure. But GNU Radio uses IQ or complex baseband signal representation in almost every block. There's support for that. And it turns out to be a very convenient representation for a number of different applications, particularly in telecom. And it just happens that if you're going to use direct conversion, which a lot of these radios do, you need complex baseband representation in order to provide all of the information that's in a signal. Back in the day, I'll just go on a bit of a tangent here. Back in the day, there was radios that were called homodyne radios. And what they would do, typically used for AM. So what they would do is they would mix the tuned frequency directly. So the LO was equal to the tuned frequency and went into a mixer and produced, a reasonable representation of an AM signal on the output that you could, detect and convert to audio and whatever. The problem with that is that the positive and negative frequencies there basically get merged into one another. They get folded down on top of one another. And while that works for AM, it doesn't work for most other more complicated signal mechanisms where there's useful information in effectively both sidebands. So complex baseband uses a different kind of mixer. It uses a quadrature mixer to produce both the in-phase and the quadrature components, and then they get sampled. And they effectively, each one of those starts at DC and goes up to, half your bandwidth kind of thing. So a radiometer is something that measures the radiated energy of something or the radiated power of something. And as I mentioned earlier, your typical radio telescope is essentially a radiometer, a single pixel radiometer. In the old days, you would do this in hardware. You'd have some RF and IF gain after your, and of course you'd mix it down to an IF or whatever. You'd have a diode detector, an op-amp integrator, some DC gain, and possibly, if you were more modern, an A to D on your computer, a relatively low speed A to D, or maybe a chart recorder. And that would be your radiometer. A radiometer in software, assuming you have a complex baseband signal flow, you simply convert the complex elements into what's called the magnitude squared. You average it and you decimate it and log it, and you're done. You have a radiometer. Very simple. And we're going to see that in a few minutes. And then a spectrometer in software. So in the old days, and actually there's still a fair number of laboratory instruments that work this way, spectrometer would be either a filter bank with lots of parallel detectors. And in fact, the spectrometer at the Algonquin Radio Observatory, as I recall, was a filter bank spectrometer. So it had racks and racks of these very narrow bandpass filters and detectors. And then all of the detectors were sampled or on a chart recorder or something. I don't quite remember. It was such a long time ago. The other approach, which is more common, is to use a swept IF or RF with a single detector. So you sweep, you have a narrow band mixer, an IF, and you sweep it across the frequency range of interest, and you kind of synchronize the output of the detector with your display, so you know where the LO is at any given point, and it gives you a swept spectrum. In SDR and DSP, typically it's done differently. You collect samples into a window of samples. You apply a window shaping function, and then you compute the FFT on that sample window, which gives you the spectral components of the signal. And then you convert that into a power. Keep in mind that the FFT's output units are in the same units as the input. So if the input is complex voltage samples, the output will also be complex voltage samples. So in order to compute the power of that, you need to square it. So that is how you compute the power spectral density. You average it and you scale it and you decimate it and log it. So that's very, very similar to what you do for the simple radiometer case, except that you've got an FFT in front of it. So why do we square our samples? A lot of people get hung up on this, and it basically proceeds from Ohm's law. The IQ samples are effectively linear proportional to the antenna voltage, the instantaneous antenna voltage. And the FFT, again, it's the same. And Ohm's law, very simple, tells us that power is proportional to the square of the voltage. Now, obviously, you're not going to know what the actual antenna voltage is, because there's all kinds of stages of gain and loss and mixing and so on. But the entire process is more or less linear. So the voltage samples that you're seeing are linearly proportional to whatever is happening at the antenna. Ultimately, for radiometry and spectrometry, we typically want power estimates. So we square the outputs, either in the radiometry case or the spectrum case. And those of you who have built radio telescopes in the past with hardware will use a diode, and you tune the input range to the diode so that it's operating in its square law region, which means that it converts an input voltage to a power estimate. It produces an output voltage that's proportional to the square of the input. The problem, of course, with diodes is that they only operate in square law mode over a relatively narrow range of inputs, and their linearity, sort of their square law linearity, if you will, tends to diverge from perfect relatively quickly outside of that fairly narrow range. And they temperature drift, and all of the other analog bits and pieces temperature drift as well. So getting to do that squaring inside software where there's none of that is actually incredibly useful. Now, what about averaging or integration? Why do we do that? So that just proceeds from statistics, and many of you already know this, and I'm probably going over territory that's old hat to you, but I thought I'd review it. So the variance in a data set is reduced by averaging over a larger number of samples. So the more samples you have to average, the lower the variance of the data set, and a signal can be caused to pop out of that data. Our signals, and I use that in quote because they're not signals in the usual sense, are often quite a bit smaller than the variance of the data set. So if the data set has a variance of let's say in dB terms, let's say has a variance of 5 dB, your signal itself may be a fraction of a dB. So you can see that if you don't do something about the variance, you're never going to see what it is you're looking for. So integration or averaging or low pass filtering is mandatory to reduce the variance. So in radio astronomy, we can achieve that in two different dimensions, one of which is the bandwidth, and the other is the integration time. So one of the reasons that professional observatories use just eye-watering bandwidths is because of this property. The variance is reduced by increasing the number of samples, and that of course means it can be, it's in two dimensions, both bandwidth and depth, which is time. So the improvement in the minimum detectable signal is proportional to the square root of those two. So ideally what you want to do is double the bandwidth and double the integration time in order to improve your signal to noise ratio, or the ability to detect very small signals. In the analog world, of course, that would be implemented with an RC and op-amp integrator in hardware. They work reasonably well, although they tend to drift and misbehave. And they've got thermal problems and all that kind of stuff. But that's all of the early work in radio astronomy, of course, used all of this stuff in hardware. The math is the same, the implementation is different. So in DSP, there's just a whole whack of different ways to average a sample stream, and they each have their pros and cons, and GNU Radio implements lots of them. The single pole IIR filter, an FIR low pass filter, there's an averaging block, there's an integrator block, and probably 3 or 4 others that I haven't even mentioned. And their differences are in their performance and the particular transfer function that they are able to achieve. And the reason that there's lots of different types of low pass filters in GNU Radio is that telecom applications typically require a huge variety of ways that they filter their signals. So that's why they're in there in GNU Radio. I personally prefer the single pole IIR filter because it's very, very cheap to execute. And you can typically implement very long integration times with a single pole IIR filter. They have some drawbacks. Theoretically, any impulse, large impulse that arrives at a single pole IIR filter affects the output forever because it decays exponentially, and at least theoretically, that impulse will influence the output forever. In reality, of course, because we're talking actual numbers in actual computers, or in the case of RC integrators, actual voltages in actual circuits, it doesn't actually work that way. But theoretically, a large impulse will affect the output of the filter forever, which is why it's called an infinite impulse response filter. Okay, so I don't think any of you have actually done their pre-work, so the next 2 slides aren't going to be relevant to you, although please speak up if that isn't true. Okay, so those 2 slides are not relevant. So what we're going to be doing today is experimenting with a flow graph, or at least wandering through it, and I'll give explanations about what's going on. And we're actually connected live to a very, very small radio telescope in my backyard. I have been the last several weeks doing experiments with a number of fairly small aperture antennas to use for sort of introductory hydrogen line experiments, mostly because it was too hot for me to work out at the observatory site and I needed something to do. So I started playing with a bunch of very small aperture antennas, one of which is currently set up in my backyard and pointed at the zenith, as you can see. It's got a roughly 35 to 40 degree field of view. It's a paragrid. which is what Sarah is currently packaging as their, I think, telescope in a box project. It's got a Sawbird hydrogen line amplifier, an AirSpy Mini, and so what I've done is the AirSpy Mini is actually out there in my backyard inside this this box here. And then there's about 3 meters of coax cable going to the antenna. The reason I did that is that if you put this right under the antenna, you get some low-level RFI. It's not that strong, but it's strong enough to make spectral plots look kind of ugly. So simply moving it 3 meters away from the antenna causes that RFI to dip far enough below the noise floor that it doesn't matter. And then I have 30 meters of USB extender going to my house and up into my office here. So that's the actual application running right now. You can see just a little blip here. I'm going to rescale this screen a little bit just to let you see the blip of the hydrogen line in the middle there. Yeah, it's barely visible now because if we look at the stellarium here, this is the zenith, and the galactic plane is moving off of the edge of our field of view. So there's hardly any hydrogen visible to this antenna right now, but there is a little tiny bit right there. So this is the application that I put together for purposes of this seminar, and we're going to be going into how it works internally. It's got two different things that it measures, the spectrum and the total power. You can see there's the total power has been going down as the galactic plane moves out of our field of view. Now, some of you probably noticed that I was able to resize this. I'm currently using the middle, my scroll wheel in the middle of my mouse to rescale that, but there are other ways to do it. There's the rubber band, so I use the left mouse button and drag a rubber band around the signal and just release it, and it rescales like that. The other thing we could do here is apply baseline correction, which is a feature inside the actual application, and it will subtract out basically the current view of the sky and give us a relatively flat line. But of course, that also just subtracted out that little tiny bit of hydrogen that was still in view. So it's no longer visible. So if I turn that off, we're back to where we were before. So baseline subtraction is a pretty useful feature to get relatively flat spectral plots that can be used in presentations and used to produce sky maps and all of that kind of stuff. The reason you do that is that any receiver, actually any receiver chain, is not going to be perfectly flat in the spectral sense. Even with something like a 1 dB tilt, which is what we see here, that's going to affect the conclusions you come to about your hydrogen response, for example, because that response is often much less than 1 dB. And when you have like a 1 dB tilt in the spectral baseline, it can be a bit of a pain. So this demo app has some a baseline corrector in it, and we'll go into that in a little while. And there's a controls panel as well, so we can set the integration time for total power, the integration time for spectral RF gain, frequency, where we're going to log our data files to, all of that stuff.
Marcus,
Yes.
is this a version of your Spectroradiometer software?
It is not.
Okay.
I started with an empty slate and built it within about a couple of hours of work, just for purpose of this seminar. It's heavily, well, it's documented internally, and it's simple enough that people can take it away and modify it if they want to, and feel reasonably confident that they haven't totally screwed it up. Yeah, spectroradiometer is a similar application with more capability to this one that I developed over the course of about a year, and it's got built-in support for differential mode and interferometry and all kinds of other things. And I didn't feel that it was suitable as a thing to dive into. So I did this instead for purposes of the seminar.
Okay. Thank you.
Marcus, is this running on top of GNU Radio Companion? I mean, that's an.
Well, it was produced with GNU Radio Companion, but GNU Radio Companion generates a Python file that you can simply run. Once you're done, you don't have to run things from within GNU Radio Companion. You can just run the Python that it produces. And that's what we're doing here. In fact, one of these windows here has the startup. Yeah, there it is. So I started it up with a bunch of parameters. Again, we'll go into that. I call it BAA seminar.py, but that's what was generated by GNU Radio Companion. And I just started it up as a Python file. So we can actually go into it now. You'll have to excuse me. This keyboard is one that I don't use a lot now, and my main laptop, the keyboard layout is slightly different, so my fingers aren't always doing the right thing. And that'll produce some error messages that that are actually just warnings that can be safely ignored. And I'll resize this screen as much as I can and take that down to the smallest possible. Maybe I'll even make that a little bit smaller. Actually, I wonder if I can. Okay. So this is GNU Radio Companion. Are people able to read the block names, the labels in the blocks?
Yes, that's
Yeah,
fine.
I can.
Okay, my eyesight is getting poorer and poorer with time, which apparently is what nature intended. So on my other laptop, which has a high def display, I actually have to use a little bit of a trick to make the fonts a little bit bigger when I'm working on this stuff. So this is what a flow graph looks like in GNU Radio Companion. There are all kinds of bits and pieces here that we will go into, and that's how this application works. Now that I can probably get rid of. Well, we'll deal with that later. So we will start here with the, if I can find it, with the source block. So a receiver flow graph, as you might expect, starts with a source. There are a couple of special types of blocks in GNU Radio called sources and sinks. And a source provides samples and a sink consumes samples. Simple enough. Some sources, of course, connect to actual hardware. Some sources are just for simulation purposes or to produce a stream of samples of a particular type. But here we're using something called the Osmocom source, which I use in a lot of my applications because it's a generic hardware interface effectively. So it supports, RTL SDRs and AirSpies and USRPs and Blade RFs and all kinds of bits of hardware so that my flow graphs can be fairly generic. They don't need to be specific to a particular type of SDR. Now I say that, but in reality, you kind of have to know what SDR you're dealing with at runtime in order to make it actually work. But the flow graph itself doesn't really need to know much about the type of SDR it's talking to. So when you're in GNU Radio Companion, you can double click on a block and it will bring up the properties window for that block. And here we see it's set up for what's called a single motherboard, and it's going to run at whatever sample rate we specify, and it's going to run at whatever frequency we specify. And there are a few other things like the RF gain and so on. These, as you noticed, are not numbers like device and samp rate and iFreq and IRF gain. They're variables, and those are variables in the flow graph, but they're also Python variables. And in fact, all of these entries here are actually Python expressions. You can put a Python expression in there and it will evaluate that expression at runtime. And so that way, that's how you make things flexible so that you can, for example, pass in command line parameters and so on, because each of these is actually a Python expression. It's not just, I mean, you can put a simple variable reference in there, which is a valid Python expression, but you could get more complicated if you wanted to. So for example, here in IRF gain, I could say IRF gain times 1.01, for example, or if I could type it correctly.
Well, Marcus, I have a Ubuntu 21.04 running in GNU Radio Companion. All I have right now is options, no title and so forth, variable. How do I even get to this point?
Okay, well, when I invoked GNU Radio Companion, I gave it the name of the flow graph I wanted to work on, which is BAA seminar.grc. I didn't think anybody had actually done the pre-work. So
I did, sorry.
Oh, is that Anthony?
Yes, it's me. I'm
Okay.
the noisy one in the group.
Well, okay, so we'll take a quick sidetrack for you and go back to the presentation because we have lots of time. So let me just do that in slideshow mode so the fonts are bigger. Okay, so this first window here that shows, a terminal session, what I'm going to have you do is open up a terminal window.
Okay.
Now, the first line you can see there is a git clone, https github.com ccra astro ra_funcs. So I have a little bit of Python that I use in a number of my applications of a bunch of functions that I find useful in radio astronomy applications. So the first thing I'm going to have you do is pull that down from GitHub with that git clone command.
Okay.
And so did that work?
Yeah, it says done.
Okay, excellent. So then you cd into that directory. So cd ra_funcs. And then you do the sudo make install.
Okay.
There will be errors, but those are expected.
What is that CD make? I'm sorry.
cd, yeah, cd ra_funcs.
Yep.
And then sudo make install. And then put in your password and.
Yep. Okay.
Okay, so now you have the RA funcs, and then you should. The next thing we're going to do is pull down this actual BAA seminar thing. So you're going to need to go back into your home directory. Just CD all by itself takes you back to your home directory.
Yep.
And then you do another git clone, as shown on the top here.
Okay.
Okay, so now you have a directory full of the BAA seminar stuff. You can CD into BAA seminar.
Okay.
And then GNU Radio Companion. And then space BAA seminar.grc.
I'm getting asked for a password.
If you're doing the sudo make install, is that what you're doing?
No, I'm doing the first line of this one.
You probably typoed.
Okay.
You're probably asking for a repo that is protected or just isn't there. So what happens is that GitHub will demand a password.
Yeah, I can't type straight. That's fine.
Okay.
Okay.
All right then.
What was that, Marcus? GUN space radio companion?
No, GNU Radio Companion, all one word. Actually, what I can do is I'll crack open a terminal window myself and make it a little bit larger for you. So,
Great.
Oops, like I said, this keyboard is screwing me up today.
Yeah, I've got one of those too. I've got multiple things going on here.
It's amazing how quickly your fingers learn one particular keyboard, and then when you go to one that you had used for years, and everything is different.
Perfect.
So that's all you need to do.
That makes it a lot easier. Thank you.
You're welcome.
Okay. Wow. Let's bring down some stuff that's done.
Yep. Good.
Oh, wow. Oh, wow. Look at this. Nice block. Okay. Cool.
Yep. So who else was trying to do this?
Yeah, I was following along, and now I type straight. It started to work, and what I'll do is I'll use your slides later.
Okay,
I can't type fast enough.
I hear you. Okay, so we have the properties block, or the properties of the Osmocom source block open. And as I was saying, all of these entries are actually Python expressions. You can put any valid Python expression in there, assuming it will actually evaluate correctly at runtime. Obviously, you can't put anything in there, but they are Python expressions. So for example, if I wanted, like here, if I wanted to take the RF gain control and multiply it by 1% before it gets sent to the radio hardware, I can do that here. Or I could call a function or all kinds of things. Any valid Python expression that is valid within the context of the executing code, obviously. So it then connects, as you can see, to this thing called a virtual sync. Now, why don't I, so I will duplicate this virtual sync. That may create an error actually, but we'll give it a try. Yeah, it doesn't like that at all. I will change the stream ID to Foobly or whatever, doesn't matter, just to remove the error on the real one. Now, when you are connecting objects in GNU Radio Companion, you click on the output here with the left mouse button, and then click on the input of the block you want to connect to, again with the left mouse button, and it produces a connection between those two. Simple. You just have to remember which mouse button to use. And again, double click on any block and it brings up the parameter window for that block. I'm just gonna remove this block because we don't need it. There we go, gone. I use Control X to remove it. Now, what is a virtual sync? Remember, I talked about sinks and sources, and a source provides samples and a sink consumes them. So a virtual sync is not a real sync at all. It's a way of making your flow graph layout more neat and tidy when you have a relatively complex flow graph. So instead of drawing actual connections between objects that may be fairly far away, sort of spatially in the flow graph as you're laying it out, you can use virtual sinks and sources just to make things more neat and tidy in the flow graph. And I'll show you that now. So we talked earlier about a radiometer basically being like a diode. You take the complex samples and you square them and you average them and you decimate them down to a reasonable rate and you're done. You have a radiometer. So I have a subgraph here, which does the radiometer stuff, which is right here. So remember, we had a virtual sink called RF1. We now have a virtual source called RF1, and it simply uses the same stream name as the virtual sink. And by doing that, GNU Radio Companion knows that this is basically a connection. It's just not drawn on the palette here, just to keep things neat and tidy. So the very first thing we do right here is a complex to mag squared. And again, we talked earlier about how when you have signals like this and the complex signals, to derive their power estimate, you square them. And there's a block in GNU Radio that does that called complex to mag squared. You'll notice that the colors of these ports change. And what that means is that the input is a complex sample. It's got both I and Q components, and the output is real, or a single floating point value. And that's because, as you see in the comment here, complex to mag squared computes the square of the I and the square of the Q and adds them together. And that produces a real floating point number. It's no longer a complex number. And that's just straight out of complex math. It's used extensively in signal processing, but it's derived from how you deal with complex numbers and derive various quantities from them. So the first thing we want to do after we have detected the signal, converted it into a power estimate, is do some integration or averaging or low pass filtering. They're all basically the same for our purposes. So the first thing we do is we integrate by a factor of 20, which takes 20 samples, adds them up, and then every 20 samples produces an output. So the integrate block in GNU Radio does both integration and decimation all in a single block. So by the time the signal gets to here, it's operating at 1/20th the rate that it was operating at on this side. And it has also been low pass filtered to a certain extent. I follow that with a single pole IIR filter, which is what I talked about earlier. Ideally, I would do this with a single one of these, single pole IIR filter. But one of the things with GNU Radio is that all of the mathematics internally, all the floating point mathematics internally is computed with single precision floating point numbers. And the reason for that is performance. The floating point unit in most CPUs is much, much faster doing single precision floating point than double precision floating point. That means you have to understand things like numerical precision and rounding problems. And the problem with a single pole IIR filter is that as this alpha value, I'll just pop up as the alpha value gets smaller, the numerical error gets larger. And there's a point at which the numerical error, just due to floating point arithmetic, single precision floating point arithmetic, causes the single pole IIR filter to fail. And so when you're dealing with samples that are coming in at, potentially many millions of samples per second, and you want to integrate those for several seconds, the alpha value tends to get very small. And when it gets very, very small, that's when you run into this numerical error. So I split the integration into two parts so that the samples are coming in at 1/20th the rate, which means that the alpha value can be much larger. So remember earlier, I talked about how any of these numerical parameters here can just be Python expressions. Here we have an example of a relatively complicated Python expression, and it makes a reference to that thing that I had you guys download called RA funcs. Well, this flow graph imports the RA funcs Python so that it can use those functions. And one of those functions is something called get alpha, which gives you the correct alpha value to use given a bunch of inputs. The first of which is the integration time in seconds, although it's actually the inverse of the integration time in seconds, because it's actually what they call a corner frequency. And then the sample rate. Now, remember that the sample rate we had previously divided by 20 in the integrate block over here. And that division ratio is defined in a variable that we call split ratio. And I put that in a variable just so that it could be played with later without having to go in and manually re-enter all of these numbers. And like I said, because of the dependency evaluator that GRC implements, that all just works. If you have, 3 blocks that all depend on a variable, in this case, split ratio, when split ratio changes, all of those blocks parameters will get updated automatically by GRC at runtime. And not just at runtime, as you're working on the flow graph, GRC is constantly reevaluating all of your Python. Every time you make a change that would require reevaluation, it gets run back through the Python interpreter and everything gets updated in real time as you do that. So notice that the single pole IR filter splits, and that's perfectly legitimate in GNU Radio. You can have a block whose output actually goes to multiple other blocks. What you cannot have is a block that has multiple connections going to the same input. You can have blocks with multiple inputs, but you can't have one input having connections to multiple blocks. So the comment here on this fast multiply constant is that the integrator doesn't reduce. What that means is the integrate block, normally when you're doing an integrator for use as an averager, is that you'll divide the output by the number of samples on the input. The integrate function in GNU Radio doesn't do that. So I simply chose to do that later on in the flow graph with a multiply constant. And again, you'll see that there's a Python expression here. The constant is we multiply it by 1 over the split ratio, which in our case is 20 because it's set by that variable to 20. So we're basically rescaling the output just because the integrate block didn't.
So if you wanted to alter that variable, that split, you would go into the directory or just use Python to alter that variable?
Well, the variable, actually, the split ratio variable is right here. We can crack it open, and there we go. There's a value field, 20. Boom, done.
Cool.
So we'll continue along the upper branch here, and then we do a keep 1 in n, which is decimation. So what we're basically saying here is we've already filtered this thing, so the information content is very low. We can drop almost all of those samples and not lose any information because we've already integrated it. By default, I integrate for 45 seconds. So you only actually, in the information theoretic sense, you'd only need to keep 1 sample every 22.5 seconds, and all of the information that's in that signal would still be there. And that's just because of because of information theory and Nyquist and Shannon and all of those guys who are no longer with us. Once we've done the keep one in N, we've again dropped the sample rate. I think, yeah, so there's another complicated Python expression in here. There's this thing called the data rate. Again, it's a variable, which basically says how fast does the very back end of this flow graph run? And everything we do operates at that rate. So you could think of it as the sort of, pre-processed data is all processed at that rate, and our decimator blocks and so on use that to calculate how many samples they need to drop and so on. Then we have a multiply constant to just multiply the output by the DC gain. I do this mostly because in the real-time displays, the number of digits after the decimal point is currently limited to 2, although I could probably find out where to fix that. So it just makes it nicer if the samples are a little bit larger in magnitude, because the real-time displays have this unfortunate property. Even 32-bit floating point numbers have plenty of dynamic range, so there's no numerical reason at this point to multiply them. It's just a convenience thing. So then we go to another virtual sink called TP out, or total power out. And where does that go? Well, I'm glad you asked. So you can see here that we have another virtual source called TP out, or the virtual source that uses a stream ID of TP out. And it again gets split between this thing called BAA data logger and BAA strip chart, and then what's called a Qt GUI vector sync. So the vector sync is a graphical object that's just part of GNU Radio that uses the Qt GUI user interface. We can see it here. If we go back into so that particular vector sync is used to display the total power. And I've configured it to show 2 hours worth of total power data. And that's what we're connecting to there. So we'll go back in here. And so the virtual sync goes over to this BA data logger thing. But what's that? So earlier I mentioned that GRC supports what are called embedded Python blocks. And they are basically first-class GNU Radio signal processing blocks. They have all the features and quirks and so on of GNU Radio signal processing blocks, but they're embedded within your GRC flow graph, basically. And you can edit the Python that forms them, right within GRC without using any external tools. So I've created a bunch of custom blocks for purposes of this seminar, and we will go into them in a minute. I want to take a very quick break, actually, and get a glass of water, but I'll be back in 30 seconds, and we will open this up in the editor and take a look at what's inside this block. Everybody cool with that?
Yes.
Oh, yes.
Okay.
I need to grab some more coffee.
So I guess you can fix all of that in edit before it goes up on YouTube anyway.
Yeah, not a problem.
Okay, so we are in this BAA data logger block. And one of the things that GNU Radio doesn't have built in, at least not in the versions I'm used to, is a way of producing sort of low rate formatted data. It has what's called a file sync block, but that is used typically for logging raw samples. That's not terribly useful when what you're wanting to do is log formatted samples for an external application like, Excel or whatever. And typically in radio astronomy, you're logging at a relatively low rate, relatively leisurely rate. So we have a bunch of parameters here. And again, they're all actually can be Python expressions, just like any other block. The formatter parameter, we're not going to go into today. It actually can optionally be a pointer to a function or a method in a class for doing the data logging, instead of using the sort of default format that this data logger uses. You can basically branch off to a completely different function that can format it in some obscure way that may be useful to you. We won't go into that, how that works today. We also have this thing called filepat, which is the file name pattern that we want to use to produce log files. We make it, again, this is a Python expression, so there's a string variable that is passed in as a command line parameter called prefix, and we add to that. And in Python, I don't know how many of you are that familiar with Python, but it's got lots of really nicely overloaded operators. So the plus operator, when you're dealing with two strings, just means concatenation. So it's basically you take two strings, slap them together. The plus operator in Python, when you're dealing with two strings, will allow you to do that. And the file extension, again, I'm just using .csv. The log time is how frequently you want to do this. Again, it's passed in as a command line parameter. I think the default is every 5 seconds. And the formatting string, that is the Python format string that is used for formatting the data items that we're producing. You could use exponential notation. I mean, you could change this to, something like 5.3e, which would produce a data item in exponential notation. I would strongly recommend people who really want to, get into this to, if they're not that familiar with Python, to do some Python learning first, because it's incredibly useful in GNU Radio to understand Python and how it works. Even if you aren't, a big time programmer or software developer, Python's relatively easy to learn, and it can really, if you want to do customizations to existing flow graphs, or branch out onto your own with your own experiments, it's very useful to learn Python just for little things like this, like how do I format a variable for printing and that kind of thing. The next parameter is number of channels. We are only logging a single channel, but this block has the ability to log more than one channel. It assumes that the data items from multiple channels are interleaved. And that's just because with embedded Python blocks, dynamically giving it like a dynamically configurable number of inputs is almost impossible. So instead, it just assumes that the input is an interleaved stream of floating point numbers. In this case, the interleave factor is 1, but for example, if you had, if this were a multi-channel receiver and you wanted to log multiple data channels, you could use this logger feature, interleave the samples before it gets to the logger, and specify, the number of channels that are actually interleaved together. Local time basically just says whether the leading time field is in UTC or local time. And longitude is your local longitude, because one of the things that this logger does is calculate the LMST and put that in the samples. So
Marcus,
yes.
on the number of channels, what would be an example of multiple data sources?
Well, let's say that you are running two radio channels, and maybe they're independent. Maybe it's a differential radiometer, and you want to log the individual channel powers and the channel difference as three different items, and you want them logged separately. Well, you could do that here.
Okay.
Now, this particular flow graph doesn't do that, but a function like this could do that. So we're going to actually go into the code, and I'm not going to, really dive into it, because that would be unfair to people who aren't computer programmers. Okay, so we've now opened up this formatter block. You'll notice that it has some stuff after it. That's just GRC's internal management. The code actually is copied into a temporary file, and you edit the temporary file. And then when you're done editing, GRC kind of brings it back into the fold. So Python is a object-oriented programming environment, or it has object-oriented features which may or may not end up being used by any given application. GNU Radio takes heavy advantage of object orientation. One of the reasons is because you may have a particular type of block that you want to use like 5 or 6 instances of in a flow graph. Well, that naturally sort of folds into object-oriented programming design. So it gets used in the embedded Python block, obviously. So a lot of the input parameters you can see are shown in the init function here. And the name of the block is here. Input signature is really important. And the way it works is that the number of inputs is defined right here. For example, if I said 3, when I saved this, there would actually be multiple inputs showing on the input to that BA logger block. I'm not actually going to do that. And the other thing is that within here, we're basically saying it's just a set of scalar values. They're not vectors, because GNU Radio supports passing vectors around or passing individual samples around. And it can be incredibly useful to do things in vectors. For example, an FFT inherently produces a vector-like output. So GNU Radio can pass around vectors. So let's say we were passing a vector into this function, and we'll actually see this with the FFT logger that I'll show you in a minute. And let's say that vector was typically 1024 big. This is what we would do. And what we're basically telling Python here is that we expect there to be a list of vectors on the input of size 1024. Now, in this particular function, we don't deal with vectors, so I'll put that back to a simple scalar. The other thing to note is that GNU Radio, when it's calling your block, it calls what's called a work function. And the work function is given a series of samples. And the number of samples can be variable. And so your work function has to be prepared to deal with whatever number of samples it's handed, and do whatever is necessary to kind of make that work. So GNU Radio might hand you a single sample, or it might hand you, 1,000 samples at a time, and you have to be able to cope with that. And this is just sort of pretty generic Python-y stuff. We're basically initializing class instance variables. Python uses this convention called self to refer to the current instance of a given object. And again, I'm not going to teach you Python today. I'm just going to kind of show you how we can use Python to do some of the things we need to do. And we have some variables here for averaging. Because we're operating at, I think 10 Hertz is what we set the data rate to of the back end. We're getting samples at a rate of about 10 Hertz, but we're typically logging, every 5 seconds or every 10 seconds or something. So we might as well average those samples as well while we're at it to produce even lower SNR data. And you'll notice here that we have this times nchan notation. So we'd have one averaging cell for each of the channels if we have multiple channels. Okay, so here's the work function that I was talking about. This gets called every time the GNU Radio scheduler decides that it has enough samples to justify calling you. It's actually more complicated than that, but you don't really need to understand that right now. So the GNU Radio scheduler calls this work function on a regular basis with some samples for you to deal with. Remember, we had a parameter called local time. We're just determining whether we're going to use local time or UTC. And the Python time function to give us UTC is called GM time for historical reasons. I don't know, there's a little village in the UK or something, I don't know. And then we have a loop, and the loop deals with all the input items and averages them and so on. I'm going over this in a very cursory way since I can't possibly teach you guys Python today. And this is where it actually writes the data out, writes the header data out rather. And so this is the LTP contains the hours, minutes, and seconds, either of local time or UTC, depending on what we picked earlier. And then again, you can see we're calling this RA funcs function called cur sidereal, and it returns comma separated values of the sidereal hours, minutes, and seconds based on, again, an input parameter, our longitude. And this actually calls the Python FM library to make that calculation. I just wrap it up conveniently inside the RA funcs. And we write some data, and then we close the file. Remember earlier I said that you can provide a formatter function. So that's why there's this conditional here that says, if we haven't provided our own formatter function, this is the default that we use. And then we tell the scheduler how many of the input items we consumed, so it can schedule output buffers and various other things that it needs to do. So most work functions end up telling the scheduler how much of the input they were able to consume. Ideally, you want to consume everything that you've been given. Sometimes you can't, so you have to tell the scheduler how much you consumed. Now, RA funcs, we might as well take a look at what's inside RA funcs. So I'm going to open that. Where did I? There it is. Okay. So the header basically tells you what it is. It's just a collection of functions that I've developed over the years that happen to be useful in a number of different RA applications that I've developed. This one is telling you it returns the fringe period for interferometry, inputs, frequency, the baseline, declination, and your local latitude, and it calculates the fringe period at the center of the fringe, or the center of the phase center of the interferometer. Get alpha we've seen previously to compute the alpha value for that single pole IR filter. This is the implementation here. And it's just a little exponential expression. And it's actually, anybody who's analyzed RC filters will recognize it because a single pole IR filter and an RC filter operate very, very similarly. And that curse sidereal that I was talking about, it does a bunch of formatting and dancing around, and eventually calls the FM library here, here, and here to give you the current sidereal time. We don't actually use this function either in the code that we're currently looking at, but this is used to, given a list of frequencies, it produces an RFI mask intended to basically be used to mask out elements from an FFT output. Again, we're not using that today, but the function is there. So that's the RA funcs. I think actually I will do this. I won't actually save it because we made some modifications, and I'll actually cancel this. So it won't actually apply any updates to that block if we cancel it. So if why don't we go back to the strip chart function here? Are there any questions? Are people totally confused now? Okay. Can people still hear me?
Oh, yes.
Oh, good. I like to check that once in a while because there's almost no audio feedback from Zoom. So, there's almost no ambient noise. So this strip chart function is actually quite simple. GNU Radio doesn't have a strip chart graphical element built in. It used to, and I wrote it, but that particular GUI subsystem was deprecated or made obsolete several years ago, and the Qt GUI folks have not gotten around to implementing that as a distinct GUI item. However, it does have this thing called a vector sync. So once you have a vector sync, you can actually have an external block do the strip chart type function. Okay, so a strip chart, as you know, is just a chart recorder type thing. And of course, we've seen it here. This total power display is a strip chart display. New samples are added at this end. And every time a new sample is added, the entire chart, shifts over by one sample. And so you can see sort of a historical data, how the data has been evolving over time. This one is updated. Effectively, it gives you seconds, and there's 7,200 seconds in this strip chart, so that's 2 hours. Now, in this case, the block has both an input and an output. And the input is a scalar value, as you can see here. Oops. You can see that it's a scalar value in the input signature. The output signature, however, is a vector. And that vector, it's a vector of 32-bit floats, and there are seconds of them. The default here is 3,600 seconds, but in the flowchart, we actually set it to 7,200. Actually, I'm setting it to 7,200 as a command line parameter that just sort of flows through. And when this block is instantiated, it gets set to 7,200 seconds. So the strip chart model is that samples are added to the strip chart at 1 sample per second, but the input to this block may be operating at a much higher rate. So we need to calculate how much decimation we need to do to achieve that result, which is what this is about. And then we just create the strip chart vector itself as a class variable. This syntax in Python is the way you create an array. It's actually a list. So you basically have the square brackets and the initial value, and then a star symbol and an integer. And that creates a list of that size of zeros in this case. It's a very common syntax in Python. It's a bit weird for me since I spent several decades as a C programmer to have this syntax and, you know, all of the sort of semantics that come with it. But I write most of my code in Python these days, and I've more or less abandoned C because I almost never need to do anything these days that requires the performance of a compiled language like C. And there's an averaging cell. And there's a work function here. It does a little bit of have we been initialized, and, you know, initializes the strip so that it, rather than being zeros on the first time it gets displayed, it's actually whatever the first input value is, just so the input display isn't so jarring. And then it deals with each of the input items. Remember that you can be handed pretty much an arbitrary number of input items, and you have to be able to deal with them. So if those input items span multiple seconds worth of updates, you have to make sure you take care of that within the block. And that's what we do here. And again, we're telling the scheduler how many items we consumed. In this case, we have to do it in a couple of different ways because of the type of block it is. It's called a general work block, which is what we use for this type of block that has both an input and an output, and the decimation rules are a little bit weird. That's a topic that would need to be explored on your own about what the various GNU Radio block types actually mean and what the requirements are. The GNU Radio webpage has all kinds of tutorial information about that stuff. So the strip chart is quite easy. We're basically just dropping a value into the beginning and shifting everything else. We actually do that right here. You can see we're actually creating a new output array based on the single input, average input, concatenated with the rest of the strip chart except for the very first item. And that's what this syntax means in Python. It's got some very, very expressive array manipulation syntax. And the sooner you learn all of that, the better your life will be, because you can do these very pithy little expressions and achieve some very interesting array manipulations while, you know, having almost no code there to do it. Okay, so that's that. We'll go back into the flowchart here. So the output of the strip chart, as you can see, the color here is the same general color, but darker. Generally, the darker versions of the colors mean that it's a vector of that type. And in this case, by default, it's a vector of 3,600 items, which of course is the number of seconds in an hour. That goes to a vector sync, which is a GNU Radio thing. It's one of the GUI objects that GNU Radio provides. Vector size, again, we use a variable called seconds, and by default it's 3,600, although the one that's running is set to 7,200. start value on the x-axis and the step value. You can control those, and I'll show you in a minute when we're looking at the spectral side of things, how to manipulate those values to give you the display quantities you want, or the axis tick values. And you can label the axes. In this case, we've labeled x seconds or time in seconds, and the Y label is detector power. The x-axis units are seconds in short form. And you can see that here. If we go into the actual running application and drag the cursor, you can see that it says 3372.29 secs and 0.06. We could have put units in on the Y value as well, but since they're all unscaled units in this particular application, what would you choose? It would be bulky to just say unscaled units and have it display unscaled units. So I didn't do anything for that. And you can set the minimum and maximum range. You can turn auto scaling on and off. You can turn the grid on and off. Number of inputs. In this case, we're only doing this on one channel, but most of the GUI blocks in GNU Radio can process more than one channel. And this update period, so it updates 4 times per second. That's how often it updates the display. That is unrelated to the rate that samples are coming in. It's just the rate at which it updates the display of that vector. And this basically says where it is placed on the display palette. You may have noticed that we have 3 different display tabs here. And there are controls on the GUI that allow you to control where a given GUI element is placed. And I won't go into the details of that. The GRC actually gives you a reasonably good description of how that works. So that's how we get our total power display. Any
Marcus,
questions?
on the average function that is on that, what the selections on that are what? Low, medium, and high, or something like that?
Yeah, I don't happen to use it in this graph, but yeah, the low, medium, high, and honestly, I have no idea what those actually mean.
Okay.
I tend to do all my averaging for this particular type of stuff outside of the display, because I typically end up needing to log it anyway. So I don't use the averaging functions in the vector display.
Okay.
So I have no idea what they actually mean, and I don't even know.
A little off subject, but in Spectroradiometer, it's got a low, medium, and high, and custom.
Right.
And when you deal with the custom, what are you? I mean, what's the range of settings there? I guess I could go into the program and see it.
Yeah, custom is I think it's just an alpha value for a single pole IIR filter, from my recollection. I haven't actually dived into that code in months, so I don't remember. But I think it's just an alpha value. Your typical alpha values for a single pole IIR are all less than 1. And the smaller they are, the longer the integration time effectively.
Right. Okay. Thank you.
So let's look at the spectral side of things. We're going to go back down here into the spectral subgraph, if you will. Again, it starts with a virtual source, the same virtual source that the total power subgraph used, because a given sample flow can be presented to multiple subgraphs in a flow graph, which is what you'd expect. Just like in electronics, you can take a signal and there can be multiple consumers of that signal. Well, same thing in a flow graph. So in this case, we are taking the virtual source and we're plugging it, the first thing we do is turn it into a vector. The reason for that is that the source coming from the radio is just a stream of samples, one after the other, with no structure beyond that. An FFT, of course, operates on a window's worth of samples, or a vector's worth of samples. So the FFT block expects there to be a vector of whatever size you're asking it to compute. So the first thing we do is this stream to vector block. And the number of items is FFT size. Vector length in this case is kind of confusing because you can, in GNU Radio, you can make a vector of vectors, and this is sort of the inner vector length. In this case, where there's a scalar for the input, and we're creating a vector of those scalars for the output. In this case, it's FFT size, which we've chosen to be 2048. I would keep it at that because of certain, the embedded Python blocks aren't really good at determining vector sizes at runtime. They'll actually fail. So if we keep everything fixed and don't change it at runtime, we're in much better shape. And then we call the FFT function. It's a complex FFT. It's a forward FFT. FFTs can be computed either forward or reverse. A regular FFT is a forward FFT. And then we use a windowing function. I won't go into all the details of this, but when you're calculating an FFT, the samples need to be shaped to produce different properties in the output estimate. Having a square shape is probably the least useful. And a square shape means that you do nothing to the samples. There's just an abrupt start and an abrupt end. Because, and it has to do with the fact that signals are continuous, but estimates are discontinuous. So there's discontinuities at the edges of any window of samples, and the output FFT estimates quality can vary depending on how you shaped the input samples. For our purposes, a Blackman-Harris window gives us a reasonable spectral estimate. So that's what I tend to use. The shift operator. So most FFT libraries, and the one that's used by GNU Radio in particular, produce their output in a format that would not really be considered natural. So the first half of the output buffer goes from DC to the highest positive frequency, and then it goes from DC to the lowest possible frequency, which is not the natural order of things. Normally you start with the lowest frequency, you go through DC, and then the highest frequency. And this is because we're dealing with a complex sample stream, which conceptually has negative frequencies. And the negative frequency is those frequencies basically below DC or below the tuned frequency, right? You have a bandwidth, you have a tuned frequency, and all frequencies below the tuned frequency are considered negative frequencies. So the normal FFT output in most FFT libraries gives you this weird formatting. If you select the shift option, the output is in what we would consider as sort of the natural ordering for humans. And so I chose this option here. Now, again, remember the output of an FFT is in the same units as the input. Samples are complex voltage samples. They're not power samples, they're voltage samples. So in order to determine the power, we have to square them. And so that's what this complex demag squared is doing. We're using the vector configuration of it. We can see here that the vector length is FFT size. And then we're using this wonderful single pole IR filter. We're just using the single pole IR filter in this case because the alpha value can be a lot larger because it's effectively the sample rate is reduced by the number of FFT bins. So a factor of 2048 in this case. So alpha doesn't need to be anywhere near as small as it needs to be in the total power case. And again, we are decimating, and we are using a calculation here, a Python expression, to determine how much do we need to decimate these vectors in order to achieve our desired output rate or event rate, which is the data rate here, which I think is 10 Hertz. I think that's what I picked. I don't know, we'll find it in a minute. Now, remember, there was a control on the GUI called baseline subtract or baseline compensate, something like that. Yeah, baseline correction is what we called it. So that actually requires that you do something to the FFT output vectors. And that's what this block here does. It makes me choose the editor every single time for every new block type. That's a pain. So this particular block is somewhat stateful. Its behavior depends on what the value of that GUI button is, which I'll just go back in here and show you. If we look at the state of the collect input to this little function that is doing baseline correction, it's true if correct baseline is false, else it's false. It's just the sense of the correction happens to be inverted in the function. So it's in one of two states. It's either collecting data to compute the baseline, or it's applying the baseline. So if it's in collect mode, then it means you're not in baseline correction mode. So again, you can see this is a Python expression based on some variables, and that the result of that expression is what gets passed into this function. So I'll just go back into that. And the work function, again, are we in collect mode? If we're in collect mode, then we basically, we're just collecting the samples and we're computing a moving average on those samples to try and get an estimate of what the spectral baseline looks like. And then all we do, if we're in collect mode, the input is basically a copy of the output. We do nothing to it because we're not applying the baseline correction at that point. So this is where we, for each of the input vectors, we just copy them into the output. There are actually underscores here, and it seems that my editor doesn't have quite the right font and is not rendering those underscores correctly. I just noticed that. But they are there, trust me. That is weird. I remember seeing that a few years ago, and it's a font issue, and I don't remember how to fix it. Oh, well, sidetrack. So if we are in baseline correction mode, then what we're going to do is take the input items and we're going to subtract out the baseline that we have previously collected and average and smooth and everything. So that'll have the effect of basically any of the ripples in the baseline or spectral artifacts or basically anything that's in the current spectral baseline will get subtracted out of the dynamic spectrum that's going through it, which of course will yield some zeros, which we'd rather not have, because the next thing we're about to do in the flow graph is compute a base 10 logarithm, and we don't want to go anywhere near zeros or worse, negative numbers. So what we do is after we've subtracted, we add back in an estimate of the average baseline. That is, if you took an average across the entire baseline, what would that number be? And we add that back in. So our baseline is still flat. It's just been raised again to roughly the average level of what the incoming signal is. And that just makes it nicer to look at and also nicer for calculations further down in the flow graph. So after we've done baseline compensation, or not, if we decide we don't want to do baseline compensation, we call the log10 function, which is a base 10 logarithm. Most most times when you're looking at spectrum, you tend to look at it in dB. It's an RF engineer's thing, and a lot of amateur radio astronomers do it as well. You could look at it in linear form, but it's very useful to basically compress everything into a logarithmic representation. Because particularly if there's RFI, the dynamic range of your spectrum can be very large, and just logging it and dealing with it in dB form happens to be useful. So that's what we do here. The log10 function is one that's built into GNU Radio. So it's basically an n log10 function. So the n is almost always 10. And then there's this scaling calculation that's just horrific. And it's just, you have to scale by the size of the FFT and the average power represented by the scaling window or the windowing function, and also compensate for the fact that you are displaying power samples rather than voltage samples. So that's what this scaling expression does. And what I tend to do is just copy it from one place to another because I can never keep it in my head. So that's what I've done here. Again, we have a virtual sink called FFT out, which is used in other parts of the graph. So there's the source half of this FFT out stream, if you will, connection. And we have two main functions hung off. We'll talk about the flipper function in a minute. There's another vector sink for displaying the FFT output vector, and a vector logger, which is basically a vector version of the logger function that we saw earlier, because we want to log the all 2048 bins of the FFT output. I won't open it up because it's very similar to the other one. It just happens to deal with vectors instead of scalars, and it only does a single channel at a time. Now, GNU Radio does have an FFT sink. So you can just take a sample stream, and run it into an FFT sink, and you can see the FFT results. We don't do that here because we are manipulating our FFT output. We're baselining it, we're potentially flipping it. So we just use a vector sink to display the resulting vector rather than using an FFT sink directly. And also it saves a bit of computation. We only need to do one FFT calculation rather than two. So the flipper function is used if you are displaying velocities. So one of the input parameters to this flow graph is whether you want to display velocities or frequencies in the FFT display function. And the flipper is used to flip the FFT output around so it's displayed in the form that is natural to astronomers, with the blue shift on one end and the red shift on the other. So the blue shift is on the lower end and the red shift is on the upper end, and the blue shift components have a negative sign, and the red shift components have a positive sign. So that's what flipper does. And it's a very simple function. Again, it takes advantage of array manipulation or list manipulation in Python to basically make this very, very easy. So it takes input and output vectors of exactly the same size. And again, so either we're flipping, that is, we're enabled as a flipper, in which case the output items are a flipped copy of the input items. And the main expression you see here is this, which basically means take all the items in that list and reverse the order. So one line, less than a line, a fraction of a line of code, and you've done the flipping operation. And it's actually more efficient to do it this way than to do it the way you would do it in a conventional programming language by iterating over all the items in the list and shuffling them around. If you learn all these Python expressions, your code will actually execute faster because it is using internal Python implementations of that are very, very efficient. So that's what the flipper does. It's really, really straightforward. And if we actually look in the actual running application in the Spectra window, you can see that it's shown in redshift rather than in frequency. And the flipper allows us to do that. So we'll go back in here to the vector sync that we are using for displaying the spectral data. You notice that the name, which is displayed at the top of the graph, has, again, a Python expression. So it's not a fixed value. It's two different string values that depend on whether we've selected the velocity option or not. So if we've selected the velocity option, the title of that graph is Doppler velocity, and if not, it's frequency. The vector size is fixed at FFT size, which is the size of rare FFT. Again, we're using some Python expressions here. The start value for the x-axis is this variable called dop_low, which is the low end of the Doppler range. If the velocity option is true, else it's the freq low, which is the lower end of the frequency range. And again, the step values are dependent on the setting of the velocity variable. And again, they're relatively simple Python expressions. And the axis labels are also dependent on the whether we've selected the velocity option or not. Now, unfortunately, you can't, some of these things you can't change at runtime. Any parameter here that is underscored is something that can be changed at runtime. And you'll notice that the graph name, the axis labels, and so on are not changeable at runtime. So they can only be changed, they can only be computed at the time that graph object or display object is created. But after that, they can't be changed. So it's not as flexible as maybe you'd like, but we've made it as flexible as we possibly can, given the constraints of GNU Radio. The update period here is every 1/10 of a second, or 10 hertz. We just tie it to the data rate. And again, that's the update rate of the display. More than a few hertz is generally not necessary because the human eye isn't going to really pick out things much faster than, a few tens of hertz. These aren't animations, they're numerical display graphs. So we don't expect to be able to follow stuff that's happening faster than that. So let's go look at some of the variables. We saw things like dop_low and dop_high and all that stuff. So GRC has variables, and they are first-class Python variables. Their values can be constants. Their values can be expressions. They can be pretty much anything that would be valid in the context of the executing Python program. Oh, actually, the data rate we have set at 20 hertz, not 10 hertz. I lied, whatever. So the sample rate is a variable here. And what you'll notice is that it's actually dependent on another variable called S rate. And S rate is a parameter that we actually pass in on the command line. When you create a GRC flow graph, just as a item of convenience, it creates a variable called samp rate. And a number of blocks by default refer to that variable. They don't have to. It's just a convenience and a convention. There's nothing particularly special about a variable called samp rate. It's just that GRC creates it by default when you create a new flow graph, and a number of blocks know that that variable is there and use it, but you can change it to other things. So we make samp rate dependent on the parameter that's passed in on the command line, which we call S rate. And that way you can configure your graph dynamically for various radio parameters just by passing in command line parameters. So Doppler is, a scary looking expression, but the bright among you may notice this this constant here and know what it represents. Anybody know what that represents? Did I lose people?
Speed of light.
There you go. Yes, that's the speed of light in kilometers per second. So what we're basically doing is we're taking the lowest possible frequency here and dividing it by the central frequency and multiplying by the speed of light, which gives us the Doppler shift in kilometers per second. So that's the low end. The high end is the other way around, and so on. Other variables that might be interesting oh yeah, so if we're displaying frequency instead of Doppler shift, we need to calculate this step size, which we could actually do as an expression inside the vector sync, but it was more convenient and tidier for me to just use a separate variable to calculate it. A lot of times it's a matter of taste and a matter of convenience and how ugly a given expression is going to look if you don't sort of break it down into external variables that you sort of pull into the expression. So the frequency step size is just the sample rate over the FFT size. And we happen to use, for purposes of that FFT chart, we do it in megahertz rather than hertz. So we divide by 1,000,000. And again, we have freq low and freq high and all that stuff. Again, it's the center frequency minus half the sample rate, and then divide by 1,000,000. So it's in units of megahertz. So again, Python is actually fairly expressive and powerful. You may recall that when we were calculating the 10 log 10, we needed to know the power of the shaping window that we used when we scaled the output. This variable calculates that. So we're actually calculating, so this internal expression here actually produces an iterative, it produces a list, and then the sum function calculates the sum of that list. And that's all that expression is doing. Again, I happen to know a fair amount of Python, and I'm not going to go into a lot of detail, but this is basically just calculating the sum of the elements of that Blackman-Harris window to use as the power estimate for the window. Now, we have a bunch of parameters here. Now, a parameter is just a variable that originates as a command line parameter. So it has most of the semantics of a variable, but it originates as a command line parameter. And this can be quite powerful. It means you can configure what it is you want to do in advance of starting a flow graph. And indeed, there are many things that you kind of have to decide in advance anyway. So command line parameters are the way you do that. And there's lots of them here. There's S rate, which we've seen in the expression is the sample rate. We default to 6 megahertz because that's one of the sample rates that's available on the AirSpy that I'm currently using. Oh yeah, we have the device parameter, which is a string-based parameter. It defaults to RTL equals 0, which is the syntax that is used by Osmocom for saying, I want to connect to the very first RTL SDR that you find. I'm running it with I can't type. So that's how I'm running it at the moment. I'm saying, please find me an AirSpy and set the bias option to 1. That turns on the bias T on the AirSpy, and the LNA that you saw in the picture is actually powered by the AirSpy itself, providing 5 volts up its input cable. But I'll restore that back to that. And again, when I run the application, I specify that on the command line. In fact, why don't I show that here? Yeah, so you can see the device parameter here. When I started the app, it says AirSpy, comma, bias equals 1. And that's a common pattern in most of my applications. There's a device parameter, and that's used to pass into the Osmocom block to describe what device it is you want to connect to. Other interesting parameters, the seconds parameter defines how many seconds are displayed in the strip chart. I configured it for 7200. Velocity is an integer, either 1 or 0, depending on whether you want to display velocities or not. I don't think that, yeah, it's unfortunate, but the command line parameters don't support a Boolean type. But unfortunately, Python knows more or less the convention that 1 is true and 0 is false. It would be cleaner if command line parameters could also support Booleans directly, where you type a string, true or false, or on or off, or something like that. Whatever. It's easy to remember that 1 is true and 0 is false. The detector multiplier is what I talked about earlier, just multiplying a fixed multiplier to multiply the total power output by some fixed value, just to make logging and display in particular a bit more convenient. And actually, we can see some of the command line parameters in the control section here. So I set the total power multiplier to 10, the integration time to 45 seconds, spectral integration time to 120. So they can be initially configured on the command line, and then you can change them dynamically at runtime with these GUI entries, which I'll show you in a minute. So here's a bunch of the GUI elements that we have, the controls anyway. The display parts we've already gone over. This is that tab widget I was talking about that allows you to have a tabbed user interface, standard GRC/GNU Radio thing. So you remember the correct baseline control. It's just a little checkbox, and it controls whether or not we're doing a baseline correction. And there's the placement directive here. It says we put it on the main tab set on the second tab, or the spectral tab. Like most things in computers, GNU Radio and Python are all 0 indexed. So the very first item in a list of things is usually has an index number of 0. There's a range widget, which you saw so TP multiplier. That's this guy here. And you notice that its default value is this variable called demult. Well, demult is a command line parameter. So the initial setting of this control comes from the command line. You can change it dynamically. And when you change it, it's basically changing a variable called DC gain. And if we look back at where we are doing that multiply, back here somewhere, yeah, this multiply constant uses the value of DC gain. And that, of course, that DC gain value comes from that GUI control, but that GUI control in turn gets an initial value from the command line. So that's another powerful pattern that I've used for years, which means you can start things off at values that you think might be about right on the command line, and then modify them dynamically at runtime to change things, which can be, super powerful and super convenient. So we'll go back to the some of these GUI items. Again, things like the integration time. This is spectral integration, which on the command line I set to a value of 120. And again, the default value is set by the command line, which defaults to 10. I've set it to 120 in our case. And other range widgets to control various other internal parameters. So we're going to look at this guy here. This is a label widget, which is just used for labeling bits and pieces on your display. And you can see here, there's this thing, LMST, which is local mean sidereal time, and is being updated once a second. Well, how is that happening? So remember earlier I was talking about abuse of the dependency evaluator within GRC and this thing called a probe function. So anytime you call a function that is dependent on a variable in the flow graph, if that variable is updated, the function that depends on that variable will be called with the new variable value. So what that means is that, for example, a GUI object like this, if its value is dependent on this dependent chain of variables and function calls, it will get updated whenever any of its variable dependencies are updated. So I kind of trick things here. I have a variable that I call TikTok. And I call cur sidereal, and TikTok gets updated dynamically at runtime once a second, and I'll show you how that happens. And TikTok is always actually 0, so that I can basically trick the variable dependency evaluator into calling cur sidereal once per second to give me the current sidereal time. And because the return value from cur sidereal is a string, I can use a Python string substitute function or method. Remember, Python is object-oriented, so most object types have some standard methods that are associated with them. Well, the string object type in Python has a replace method associated with it that I can use for replacing elements in the string. In this case, I'm replacing commas with colons because the cur sidereal function returns some comma separated values. Okay, so there's this variable we call TikTok. And how does it get updated? Well, TikTok is itself dependent on a variable called pacer, which we just multiply by 0. So it's always 0. Well, what's pacer? Pacer is one of these things called a function probe. And a function probe is used to call a method or a function on an existing block. It has to be a signal processing block. And it calls it at whatever rate you want. In this case, we're calling it at 1 Hertz. And we're calling the level function on pacer probe. What is pacer probe? No, pacer probe was actually back here somewhere. It's attached to the signal flow, and it's a probe signal block. And it, oh, you know what I forgot to do? I forgot to turn on show all block IDs. When you're in GNU Radio Companion, turn that on because it allows you to see the object names that have been assigned to the various blocks. 99% of the time, it isn't important. You don't need to know what object name GRC assigned to your object. But in the case of objects like this, where you need to know their object name because some other thing needs to be able to call it, we need to know what its ID is. So in this case, we called it Pacer probe, and it's a floating point probe, and it is connected to the flow, but nothing comes out of it. So a probe block is a block that simply consumes samples, and every time its level method is called, it returns whatever the value is of the sample that has currently passed through it. This can be useful for low-speed processing. And in this case, this thing is being called by the function probe that we just looked at. This guy here. Notice it says block ID Pacer probe. Well, that's the block ID of that probe block that we just looked at. And it is calling its function called level, or its method called level, once per second. And that is returning a value, which we don't end up actually using. We're simply using this sort of polling framework, if you will, to allow us to update this GUI label once per second. And that's the only instance in this particular flow graph where we use this feature. In other flow graphs like Spectroradiometer, I make much more use of it to do actual real things. And when I finally port Spectroradiometer to GNU Radio 3.8, I will change it to use embedded Python blocks wherever I can to do this sort of thing. But here, we're just using it to update that LMST label. Any questions on that? It's a bit subtle, and it kind of requires understanding what dependency evaluation means and how that might actually pan out in a real flow graph. It can be instructive once you know a little bit of Python to actually look at the code generated by GNU Radio Companion to see how exactly it does a bunch of these things. So we're going back into the flow graph here, and what else do I need to show you? We have some more label widgets here, like in the control panel, we say what our logging prefix is. It says, oh, we're currently logging to this logging prefix. Not actually that exciting. And also we have a label on the home page, if you will, that says this is the BAA seminar for September 18th, 2021. That could be anything. We could pass that in. If you had multiple instances of this running, for example, and you needed to be able to identify the different ones, you could have this value here be passed in as a command line option. In fact, why don't we do that now as an example of how to do this? So let's call the default value, let's call it title. Hopefully that isn't a restricted variable name. Okay, so we called it title, and let's create a command line parameter somewhere. Where did all my parameters go? They're up there somewhere. There we go. So we'll create a command line parameter. Oh, GNU Radio Companion supports cut and paste. So if I want to cut and paste this block, I use Control C and then Control V, and I have a duplicate of that block. And we're going to change it to title, and we're going to say label / title for running graph, and it's going to be a string value, and we're going to call it that's the default value, would be BAA seminar 2018. Actually, no, let's make it something else so it's obvious. So now if we go back to that bit of GUI widget, if we go here, It says my title here. Actually, we could make this a variable too. The way it's displayed is that it's label colon and then the label value. We only change this part here. So if we look at the actual running, this part here will still say BAA seminar, and this part here will be whatever we configured on the command line. We could make it fancier and put a variable here and have it 2 parts, all driven by the command line. But you kind of get the idea. I hope you kind of get the idea. Trying to see if there's anything else here we need to cover. Why don't I just open it up for questions?
I'm fascinated by your TikTok and how the variable dependencies work.
Yeah.
At one point, you did a plus with the TikTok, and in another case, you had a multiplication. Is there a performance issue there? Is
No,
plus
no,
just a little simpler?
No, I'll show you why. We need TikTok. So we need TikTok to always be 0. And the value out of Pacer is going to be some small floating point value that is the current detected power, because we're happy to use the probe block on the total power subtree just as a convenient thing to probe once per second. But we don't care what his value is, and we need his value to be 0.
That makes sense. Thank you.
Now the second part of that is that you'll notice here that we add TikTok. The reason TikTok has to be there at all is that will trigger the dependency tree, so that anytime TikTok is updated, this particular expression will get reevaluated every time TikTok is updated. But we don't want longitude to be changed at all. So we add, if we multiply by TikTok, the longitude would always be 0. If we added TikTok, the longitude would always be the longitude. Does that make sense
to me?
Okay.
Yep, that does it. Thanks.
It's a bit of an.
Sorry.
Go ahead.
No, carry on what you were saying. I'll come back.
It's a bit of an abuse of the dependency evaluator. I don't think the designers ever had in mind that it would be used this way, but I'm not the only person who uses it this way. It turned out to be an incredibly useful feature in ways that the designers never really contemplated. And that's fine. That's the way you want these things to unfold as time goes on. You invent a very simple thing and you go, wow, like it's being used in all kinds of ways I never anticipated. It does somewhat, violate some of the data flow, model of GRC, but really it's incredibly useful. And when there were moves made to kind of remove that functionality, there are various people like me who kind of stomped our feet and said, no, just because, you learn. A lot of the people developing GNU Radio are relatively young and have only graduated, relatively recently from school. So they learn an awful lot about the purity of a given concept, and anything that violates that purity, they feel should be stamped out. Well, the real world is much more pragmatic than that. In the real world, things are a bit dirty. In the real world, the edges are a little bit fuzzy. And as a programmer, you gain maturity when you realize that. You realize that not every pure concept you learned in school is always going to be as pure as you learned it in school. So the reason I had people install Ubuntu 2104, which is not a long-term support release, is that the version of GNU Radio that was in 2004 had this issue where you could not refer to these block names because GRC hid them because of, conceptual purity reasons. And the developers more or less immediately reversed that decision. The problem was that they'd missed the packaging window for Ubuntu 2004. So GNU Radio 3.8.1, I think, is what made it into 2004, and it had this very bad decision in it and then that decision was reversed, but that didn't make it into the 2004 packaging window, so it had to go into 2104. So that's why I had people do that, because otherwise we wouldn't have been able to show this little trick. And in fact, there would be no really convenient way to do that sort of updated label widget in any really convenient way other than by using this trick. Because GRC is this whole, data flow model, and it's not procedural. We could have edited the generated code and made it work, but that's something that is becoming less and less appealing, even though I've done it in the past. And as GNU Radio features move on, it's becoming less and less necessary to edit the generated code to implement features that simply aren't achievable using the data flow model. So
I had a couple of questions, if possible. First one is that in the lead up to all this, I noticed there was something about not being able to use like a Raspberry Pi for this, and I guess it's related to the things you were just talking about. Is it the implementation of GNU Radio in with a sort of Raspberry Pi 4 or something like that?
I lost most of that.
Oh, have I gone unstable or something?
Very, very stable connection here.
We heard you.
Yeah. Wait a minute, maybe I was hovering. Probably I was hovering over the mute button.
Oh, maybe.
Can you hear me now?
Yes.
Yeah. Oh, right. No, when this was advertised, we were advised that we couldn't use a Raspberry Pi 4 or whatever. I mean, is that related to the varieties of new radio implementations you're talking about?
Well, I don't think it would be a very satisfying experience because of the performance envelope of a Raspberry Pi 4, and because the versions of Ubuntu, for example, that may be packaged ready to run on a Raspberry Pi 4 may not be as up to date as those that are packaged for an x86 laptop, for example. That's not to say you can't. It would just be inconvenient, and there would be performance issues probably. Like running at more than a few megasamples per second on a Raspberry Pi 4 and maintaining the GUI interface may not work. There just may not be enough CPU cycles there to make it work.
It is a bit painful running on a Raspberry Pi 3, just talking to a sound card. So
yes,
yeah, I think you're probably right on that.
Now having said that, I have a semi-commercial Radiometer implementation that runs on an Odroid XU4, which is kind of in the same performance envelope as a Raspberry Pi 4, and it supports a GUI, but the sample rates are quite modest. They're like less than a megasample.
Right. I just wanted to ask a hardware question about the demonstration you're doing.
Sure.
I noticed on the Nolec Sawbird site, there's the bare bones version has a 50 ohm load you can.
Yes.
I wondered if you'd use that as well as the one that doesn't have it, and whether it helped.
I did use one. I actually helped develop that particular thing, and so I had some beta samples a couple of years back, and I did use them to stabilize total power observations at our previous site. But the problem is the effective noise figure on those is quite a bit higher, which was a surprise to all of us because we settled on a series of components that would actually give us a quite good noise figure, even though there's an RF switch in the way between the antenna and the LNA. But despite what we thought was fairly careful component choice, the noise figure was about 0.3 dB higher than we were expecting. So it was a disappointment in that regard. And the other thing, of course, is that the 50 ohm load is on the board, which means you have to keep the board at a fixed temperature in order to get reasonably good stability out of it. So I did do an implementation of a switching thing that that allowed us to switch. I found that because of the increased noise figure and the fact that you had to keep the terminator at a very stable temperature meant that our recordings weren't anywhere near as stable as they could be.
So you lost the purpose basically of having the switch load effectively.
Yeah, it doesn't work as well as you might hope unless you do a lot of engineering outside of it to stabilize it.
Right. Okay. So your recommendation would be to go for the package one that doesn't have the
yes. The noise figure on the package one is better, and really the real way, I've always maintained this, the real way to get sort of stable radiometry-like measurements is to build yourself an interferometer. They don't suffer from the game stability issues that a radiometer does. Basically, the output, you'll only get output if the input correlates, if you're using a correlating interferometer. So that's the way to proceed, in my opinion.
Fascinating. Thank you.
Marcus,
Yep.
At the start of this presentation, you made a comment about performance being related to the vector capabilities of CPU.
Yes.
I just wondered if there was a particular sort of hardware platform looking at the sort of single board computer type thing. I tried a few years ago to get stuck in with GNU Radio and a Raspberry Pi, but this was a few years ago, and I failed
Sure.
miserably. I just wonder if the Raspberry Pi sort of family is really suitable given that the CPU architecture.
Well, I'll say this: if you produce flow graphs that are just for processing without any GUI bits and pieces, then a Raspberry Pi 4 or an Odroid XU4 will be adequate for lots of different tasks. Absolutely. But once you try to get your SBC, particularly if it's an ARM-based SBC, to do all the graphical bits and to run your signal processing, you'll find that it starts losing samples and that sort of thing. There are a lot of flow graphs that I produce that have no GUI bits and pieces at all. There's no requirement that you use any of the GUI bits and pieces. You can have a straightforward no GUI flow graph that just does processing and logs data to a file. And you'll be able to make that work on a Raspberry Pi 4 up to probably several megasamples input rate. That shouldn't be a problem. But once you get fancier and you want GUIs and all that kind of stuff, then you have a problem. So the model that I use with single board computers is that they mostly run with no GUI, and I have some kind of central computer that kind of orchestrates observations on all of these single board computers. Like our dual polarization spectrometer that we run, the actual radio processing is done on a pair of Odroid XU4s, and they send summary data at a few hertz to a central computer that processes them a little bit further and then logs them. And there's no GUI on those at all.
Marcus, I got a couple of questions.
Sure.
On the alpha for the IR filter,
Yep.
is that 1 over the number in hertz or megahertz?
You know what? It ends up being very close to that. When you actually do the math, it ends up being very close to that. But I used a formal expression for a single pole IIR filter from a textbook, and I just happened to package that up. But when you compare basically 1 over, let's say you want a 1 second integration time and your sample rate is a megahertz. Well, an alpha value of 1 over a megahertz is very close to what that alpha calculator will produce.
Okay, and the other question is, you mentioned about having a window function on your FFT.
Yes. Yeah.
What benefit does that have when we're just looking at our noise signals?
When you're just looking at noise signals, I don't think it has that much of an effect. when you use a square window, you can get these edge effects that are unpleasant. But yeah, the window functions are basically used to kind of tailor the sort of fine details of the spectral estimate that you're getting. And they control things like how much spectral leakage there is, like between bins. So some windows produce more spectral leakage than others. And that's a whole subtopic that can, you can read up about it in textbooks and online and so on. So the different window functions have different, very subtle properties in the spectral estimate. If you're just looking at noise, if you don't expect there to be any distinct spectral features, then it probably doesn't matter. If your input really is just randomly distributed noise with no spectral features at all, no, it absolutely doesn't matter.
Okay, thanks very much.
I have a last non-technical question. Where can you go for real introductory documentation so that you can get a feel for how this thing works and what it does and the concepts behind it?
There's a lot of tutorial information on the GNURadio.org website, and there's tons of documentation, much of it technical, I'll admit, but there's also an entire section dedicated to background tutorials.
Okay.
And pointers to other websites. For example, if you don't really know what digital signal processing is, the GNU Radio website has a pointer to other people's tutorials on the subject.
Okay, thank you very much.
So that, I think, is it for me, unless there are any other questions. Feel free to download and play with the BAA seminar thing. If any of you come up with really cool extended features or changes to it that you think should be incorporated, particularly in the context of our next tutorial in January, we'll probably start out with this as a base and add to it. We're going to add interferometry to it. Just let me know. I mean, I can merge in other people's code, no problem. And there's a concept called a pull request on GitHub where you create your own fork of the code, work on it, get it working the way you think it should be, and then you send me via GitHub something called a pull request in which I review your updates and then decide whether or not to fold them into the main feature. So we can all kind of collaborate here on developing this thing if we like.
Well,
okay,
thank you.
I think we are done.
Awesome.
Yes, thank you very much, Marcus. Are there any more questions? I would hate to cut this. I'd hate to cut anybody off.
I've got a quickie on the stuff to download. I think I missed that, and I did try to download it when I saw Marcus's slide and follow it then, but I just wasn't quick enough.
Okay, so
is that around?
Yeah, well, so I'll go back into my slideshow here.
Okay, let me just photograph it.
Marcus, perhaps you could put it in the chat because there's already the link to the GNU Radio tutorials there, which make it useful.
Well, actually, I can put a link to the entire presentation in the chat window. Let me.
That would be great.
Actually, it's sitting in a place right now that people won't have access to. So it will take me. Why don't if I mail you the presentation or a pointer to the presentation, can you distribute it to the others who signed up?
I can do that. Yes.
Okay. I think we'll do it that way because right now it's sitting in an inaccessible spot.
Yes,
So,
of course.
Yeah.
Thank you.
Marcus, thank you very much. Some of us have got a bit of homework to do before January, part 2, but
yes.
That was just fantastic.
Oh, good. I wasn't sure, how to set the kind of level of what it was I was going to do, and I'm glad it was the right level.
Yeah. That's great. And I'm sure there'll be many people viewing this on YouTube. We had one guy from Australia that couldn't see the end because it got so late he had to go to bed. But yeah, thanks again, and we look forward to catching up with you for part 2 in January.
For sure.
Enjoy your lunch or supper.
Yeah, lunch, I think, at the moment. Yeah.
Lunch for
Well
you.
done,
for
Marcus.
us.
Really enjoyed it.
Fabulous. Thank you very much.
Oh, you're most welcome, everybody. Talk to you later.
Thanks.
Bye-bye.
Bye.
Bye-bye now. Bye-bye.
Bye. Cheerio.